the main metrics that are of concern for circuit design, and these metrics include delay, noise, اللي هو إنه circuit is robust, the power, but also more importantly, before all of these comes the, sorry, I didn't hand touch the iPad. Before all of this comes the cost or the yield of the design. So هيدول design metrics بنسميهم, they are important for us. We're going to look a little bit at the cost analysis from a company perspective, from a yield perspective, and then we will start to give you some basic definitions. And these definitions you have seen before in courses like 310 and 311. So it's meant to be a refresher. But then as we tackle the topics separately, we're going to elaborate more on them. يعني مثلا حنراجع, we're going to review the RC time constant, then we will use it later when we study the delay, we find the effective resistance of the circuit, etc., etc. The other things that this is going to tackle, it is going to tackle some more general definitions, and these general definitions are related to the metrics. Yani for example, when we talk about what does fan out mean, what does fan in mean, these are terminologies that are used in circuit design that we will cover. And I'll fan out مثلا how many loads I am handling, fan in how many inputs I have, and these will pop up along with a few other definitions that will come here. Towards the end of the lecture, we will talk about the ring oscillator structure, okay? And the ring oscillator structure really is nothing but a series of inverters connected together that can create some signal with which we can measure the frequency. So basically, this lecture is meant to be a high-level review with some technical terms that might seem a little bit condensed, but eventually we're going to reuse them throughout the lectures. So it is meant more to be a flashback to the previous topics, okay? So this is what this lecture is intended to be about. Okay, so let us start first from the main and major concern that companies have, which is cost. And this will be the only financial but yield analysis related lecture that you will see in this course. Eventually, everything is cost driven. A company will not fabricate a chip if it is losing money. Type great. We're gonna divide the cost of fabricating the chip into two components. The non-recurring engineering cost, and for example, Apple is coming up with the new iPhone. So what it does is that the engineers will sit there for 6 months. They will have the design ready. Once the design is ready, it goes to the fab. And in the fab, every phone or every chip for every phone that is being fabricated will have its own cost. So there are two types of costs, the non-recurring engineering cost, okay, and the NRE is basically the non-recurring, the time which all of these engineers spend for 6 months, but this gets amortized or distributed over all the components. And then there is the recurring engineering cost, which is the cost of the parts, the assembly and the testing. Yani كل chip needs material, and then the material, once it is finished, it is tested, and then once it is tested, if it passes, so once we do the testing, the chip might pass or it might fail. And if it fails, we're going to discard this component. So really, if the chip passes, this is the chip that we can make a profit from, and that's why we have to test each and every chip in our design, okay? طيب, great. Let's see now what comes in also. Now, in addition to cost, okay, which is the non-recurring engineering cost and the recurring engineering cost, there are other fundamental metrics that we worry about, which are the reliability of the design. My design has to be reliable, meaning it should operate. If it does not function, if the temperature is a little bit hot, or if it fails to function, if it is subject to some noise from another device, this means that my circuit is not robust. Plus, we care not only for noise from external devices, we care about intrinsic noise within my device. Yani the device itself will be comprised of many components, many little components operating. When these components operate together, they should be sustainable and they should be reliable enough that one should not inflict problem or error on the other part or other component within that chip. So reliability and robustness to noise is a very important metric. Now, if I can fabricate my chip, it passes the test, then if it is reliable when it is in the field, what matters to me most is that it performs well. By proper performance, this means that it meets a certain speed or delay criteria, and it requires a small amount of energy, so the battery can last long enough, okay? Why speed is important? Because we wanted to finish as many functions per second, as many ops per second as possible. And typically, for example, when Intel sells its chips, it will have them in bins, tested and placed in bins. Let us say that some of them operate at 3 gigahertz, some of them operate at 2 gigahertz. Okay, the price that it will require for a 3 gigahertz processor will be much higher than the price that it is going to require for a 2 gigahertz processor. And this means that we care that the chip design, the better it is, the more I have in this stack here, the better for me as a profit as a company. And for me as a consumer, the faster the design, the faster I can get my processes to be done and finished and my operations to be executed. Hala, power consumption is very important for two reasons. Because of the heating, we don't want it to consume too much energy because it can get heated and corrupted. And at the same time, we have lots of portable devices, as you know, nowadays. So the longer the battery life, the better the product is. Yani you will not buy a phone with whose battery dies every 1 hour or that needs too much charging. You will buy the phone whose battery lasts longer and can perform more and more operations. Okay? Yeah. These are the design metrics that are fundamental and are necessary for any company to have a successful product. Okay, any questions? Okay, great. Let's go now to the next slide. Hala, in the coming few slides, we are going to talk about the cost of integrated circuits. مثل ما حكينا إنه non-recurring engineering cost, it is a fixed cost to produce the design, to come up with the map. يعني it's exactly like somebody is designing a map for a stereotype car or for a stereotype house, and then this will be executed or fabricated, and for example, BMW will come up with many cars, the same Intel will come up with many chips. The cost is influenced by the design complexity. And if I'm building a chip for a server, it's different than a chip that will be embedded in a camera, for example. And the designer productivity, that's why we care for the best engineers. And it is most pronounced for small volume products. Yani, for example, IBM sells the P series servers or the Z series servers. And the Z series servers go to the big banks in New York who have these large, huge operations, but they sell a few And when they sell a few, they can cost up to millions of dollars. And they have been using the same designs because they are, of course, migrating them to the newer technologies because they are very robust and very reliable. So if I am a bank that is running a worldwide operations, I cannot afford error. I am going to ask for a very custom-based server that has been working and running perfectly for me, but because I'm producing as a company a small volume, then I'm going to charge a lot for this. Bainama, if we are producing millions and millions of chips, then the design cost will be amortized across all of these chips. Hello. The recurring cost, as we discussed, is proportional to the product volume, how much I'm going to fabricate. It anchors how much cost I need to fabricate the chip from silicon to realize it to a chip, yani from the sand to silicon to chip. And also it is fabricated, we'll talk about fabrication in other lectures. It has to be assembled, packaged, and it has to be tested. And a bad chip will be thrown away. Okay, so these are the costs of the integrated circuits. So therefore, if we want to amortize the cost per chip, okay, it is the recurring engineering cost plus the non-recurring engineering cost over the number of functional chips. هلا بلشنا نحكي عن اليد. What does the number of functional chips means? This means that if I fabricated 100 chips, and they all underwent testing, I get 90 that pass and 10 that fail. This means that the number of functional chips is 90. And also we put a definition. This means that the yield is the number of pass over the number of chips. And this means that it is 90 over 100, it is 90%. فبلشنا نحكي هلا عن ال yield. Great. So if I want to know the cost per integrated circuit, it is the cost for fabrication plus the engineers, how much they costed me over the number of functioning chips. That's how we amortize it. Okay. Any questions? Okay. Great. Hala, let's look at this figure a little bit and see what we see here. This is a wafer. It is a wafer that comes from a fab. We will see in other lectures that the engineers get a barrel of silicon material. They're gonna slice it, cut it into thin wafers, like the small wafer in the biscuit, but they are wide wafers. They have a large diameter, typically 30 centimeters the diameter is. And on this wafer, we print many chips. Yani, let us say I have my chip comprises an inverter. Okay, so we rely too much in fabrication on parallel processing. So we print many of these inverters. Okay, and each of these blocks represents what we call a die. The die is the unpackaged chip. It's the flat design, okay, without pins, without plastic packaging to protect it, okay? And once this is printed, if you can see here, this is the die. It is very regular. We can see many components, many connections, buses, and stuff like that. Then we cut it and then we package it into chips with pins and we perform the testing at different stages. We perform the testing for the die itself and then we perform testing to make sure that the pins and the package is working, and then we obtain that chip that we are after. Hala, this is how the integrated circuit becomes a packaged chip. Great, let us see what is the cost of die fabrication. It is the cost of the wafer over the number of dies per wafer times the die yield. هلا بلشنا نفكر إنه أنا if I have a wafer let us say on the wafer I have 360 dies, okay, and then the yield is 90%, okay, then we get the total number of functional chips, right? And therefore, the cost of fabrication is equal to how much the wafer costed me divided by the number of dies per wafer times the die yield, okay? So let us now look at this here. Hello. Like every process, okay, there are defects. But first, before the defects, let us look at the number of dies per wafer. So the wafer is circular shaped, okay, and the die is square shaped, right? So if I want to fit a number of dies, if I tell you how many dies per wafer I have, you will tell me it's simple. I'm going to divide the area of the wafer, which is pi r squared, by the area of the die. Okay, we're gonna say we have to subtract a factor to compensate for these peripheral wafers, that dies that are not perfect, that cannot fit into this wafer. So this is the component where we subtract this factor. Okay, so it is related to the pi diameter, اللي هو circumference, divided by √2 the die area, which is somehow related to the sides or the diagonals of the die. Okay, so we find the number of dies wafer by dividing the die area by the wafer area by the die area and subtracting, compensating for the difference in the shapes. Yes, different ICs can be printed on the same wafer. So sometimes what they do is, for example, we can squeeze in between the white spaces. Let us say this is a big chip. I can plug in here some small dies that can still fit in. That's why when a university, for example, is collaborating with a company, typically the university folks or the research folks ask the product engineers, can you squeeze in this new design for me? I want to test it. And typically they rely on what they call the white spaces here to fit in these designs. Okay? So let us now look at the implications of the die area and on the yield, or how the yield is related to the die area. When you work in a fab, they call it a clean fab because to us the transistor is a nanometer design. It's very small, as we discussed last time, and the dust particle, just like the hair circumference that I showed you last time, can come and fall on the chip, and by mistake it can short two transistors together. If it shorts two transistors or two wires together, it is called a hard defect. Why is it called a hard defect? Because I cannot fix it, neither by increasing the voltage or lowering the temperature or anything. So the chip practically has to be thrown away because I cannot guarantee its functionality. Type. We control the environment for fabrication, but we cannot control it perfectly. Let's look at the left-hand side design. Here I have 1, 2, 3, 4, 5, 6, 7 defects. These defects have fallen on the wafer area, okay? And once they have fallen onto a chip, I cannot use this chip. It is most probably going to be thrown away. Chances are when I'm going to test it, it is going to fail. Okay, and there's nothing we can do about it. So the yield here is 25%. Okay, now let us look on the figure at the right-hand side. The same 7 defects fell on my chip, but my die area is smaller. So what are the implications on the yield in this case? What do we see here? Is it going to be larger yield or smaller yield?
Larger.
It's going to be larger, right? So if we calculate this, the yield will be approximately, let us say, 20 over 25, which is like 4 over 5, which is around 80%. Okay, so the yield has increased. That's why when we build a design, we try to target to have the design as compact as possible, not only because I can fit in more chips on the wafer and therefore I can make more money because I can fabricate things faster, but also because I can guarantee that my yield is much higher. Okay, so that is one important design requirement that we have to keep in mind, and that drives lots of design effort. Anybody has any questions on this slide? طيب, okay. Let us look now at this equation here. So the die yield is equal to 1 plus the number of defects per area, okay, times the die area over alpha to the power minus alpha. هيك نشوف. طيب, the designers wanted to predict, and in this one, for example, in Samsung, there should be some metric related to how clean the environment is, to their whole fabrication process. بالنهاية, the fab is like a wood factory, or it is like an iron factory where things fly around when you cut, wash. They try to control it as much as possible. They try to keep a clean environment, but every environment will have its own defect rate. So they summarize this defect rate into the defects per unit area. Okay, so هاي هنسميها DR or defect density, DD. Okay, and then they said, well, طيب great, the defects, number of defects per unit area times the die area, okay, will tell me how many defects I can expect inside my die, right? يعني أنا if I have the defect density, for example, it is equal to مثلا 1 per centimeter squared, and my die area is equal to 2.5 centimeters squared, chances I'm going to have 2 defects in my chip, I'm dead. My whole design is going to fail. But if my defect density, we called it here big D, so let us be consistent. If my defect density is now equal to, let us say, 0.1 per centimeter square, this means that if my die area A is equal to 2.5 centimeters square, D times A is going to be equal to 0.25. So chances are I will have a quarter of a defect, or in other words, every 4 dies, I will have 1 defect in them. So I'm in a better shape. Okay, and then they scale this by a constant called alpha, and this constant alpha is really property of the fab, and they agreed that it can be around 3. And now what happens to the yield? كل D times A. Okay, so here in this first one, D times A كانت 2.5, and here D times A is 0.25. So كل D times A, as D times A increases, the yield is going to decrease, and vice versa, صح? كل ما يكون عندي chances أكتر to have more defects in the die, then the yield will be dropping, and that's where the power to the minus alpha is. We will remember this equation. We don't have any. It will be provided to us, this equation. So let us look at the graph here that we will see here. هات نشوف الجراف that we will see here that shows the relation. So as you can see here, this is the yield in percent, and the axis is D times A. The larger it is, the smaller the yield is going to be. So كل ما كبرت هيدي كل ما الييلد رح يصغر. So هدفنا نحن يكون في كنترول على الفاب ويكون في كنترول على الاريا. Okay, so let us look at this example here. In this example, it is giving me that the wafer diameter is 30 centimeters. The die area is 2.5 centimeters square. The defect density is 1 defect per centimeter square. And the wafer معنا إياها. And they gave me alpha, which is a constant representing the fab. Okay, so the first quantity that I can find, let's see what the questions first are. Okay, so the first quantity that I can calculate here is the number of dies, right? So how many dies do I have? The number of dies that we're going to fabricate is going to be the wafer area يلي هي pi r squared يعني pi ضرب 15 squared, okay, over the die area which is 2.5. The two units are centimeters squared, so we are fine, minus the wafer perimeter اللي هو pi r على some constant اللي هو root 2 times the die area. Okay, and this tells me that per wafer I have 240 dies. Okay, مثل ما حكينا الwafer is round and the dies are square. Great. هلا بدنا نطلع الييلد. Okay, so الييلد قلنا it is 1 plus D times A اللي هي 2.5 times 1 over alpha اللي هي 3 to the power minus 3. And if I calculate this quantity, I will end up finding that my yield is 16%. يعني out of every 100 wafers, I'm going to have only 16 without defects, meaning 16 will be functional, and therefore net 240 wafers بضربها بالyield اللي هي 0.16, I find out that I have only 38 wafers per die. Dies per wafer, sorry, that are going to be yielding. So here I'm losing a lot, and it takes time and money to fabricate these, and I'm throwing more than 3/4 of them away. So my process definitely needs to be fixed. Okay, so or I'm going to charge my customers a lot of money. Okay, so the die cost is a strong function of the area, and this is why we look at minimizing the area and we try to fabricate our design with simple regular gates. Yani going for big and complex components is only going to increase the cost of my design, and we will learn this throughout the semester. Okay, anybody has any questions about this example? Okay, great. Let's look quickly here at this chart. This is from the 90s. It's showing us designs that are small all the way to designs that are large, like the Pentium or the Alpha processor, which and the HP processors, etc. And let us look here. Now, the number of layers is related to the complexity of the design. Let us focus on two things: the wafer cost, the defects, and the area. Defects is property of the fab. Yani this fab is a good fab, this fab is a weaker fab. Okay, and then let us look here at the area of the chip. This is the largest. Okay, this is the smallest. And this is the smallest defect, and this is roughly large defect number. So we can see that when the defect and the number of defect density and the area are small, the yield is high, whereas when the defect density is high and the area is large, the yield is very low, it's around 9%. When the area is larger, the number of dies per wafer is smaller, and therefore the cost of the chip is going to be very large to the customer, as opposed here the cost of the chip is very small. طبعا the Pentium has more functionality, so it costs us more at the customer end and at the company as well. Okay, so هيدي بس هيك generic example to give you a practical example. هلا we talked about fabrication, we talked about cost. We're not going to dig into the three concerns once the chip is functioning and is fabricated that we care about. Its robustness to noise, its speed or delay consideration, and its power consumption. Okay, here I'm showing you an example or a small circuit showing the inverter. Hopefully you remember it. If I input a 0, I will get a 1, and if I input a 1, I should get a 0. Great. What is the definition for noise? Noise means I'm getting unwanted variations of the voltage or the current at the logic nodes. Okay? يعني the 1 is not a perfect 1 or the 0 is not a perfect 0. So the first question that we ask ourselves, where does noise come from on a chip? Okay, let's look here. We have different components on the chip. Two wires can create a parallel plate and there can be capacitance between them. The wire itself, if it is long enough under certain frequency of operation in a certain layer, it can have its own inductance. And of course, all wires have their own resistance and parasitic capacitance, as we will talk about within the chip, small and large. So what can happen is that I can have capacitive coupling from a wire sitting next to my input. And of course, if this wire signal changes, any capacitor will have a current which is equal to C dV by dt. And we will see some current that is going to be injected here and perturb my signal. نفس الشيء. So the voltage change on one wire can influence the signal on the neighboring wire. Okay, and this is a big field of study and we call it crosstalk. Keep when we are talking on the phone and we say in the old days, if you ask your grandparents and they say, oh, I can hear somebody else talking, this is why they call it crosstalk, because the signals couple. Inductive coupling, the current change in one wire can induce current or influence the signal on another wire. And then resistive coupling, by this we mean that we will have resistor drop. ليش؟ لأنه the signal when it is arriving from this node to this node, it is not ideal. So I typically want to have the same voltage on all these three, but I might have voltage drop. We don't notice it for the small signals, we notice it for big signals like the power grid or the clock. Okay, so noise can happen due to many sources on the chip. But as well, as we said, we can have bounce on the grid, يعني the VDD when it is or on the ground. We can have voltage drop on VDD or we can have bounce on the ground. So the ground might not arrive to me as a perfect 0 and it might not arrive to me as a perfect VDD because of this coupling that happens in the circuit, because of the IR drop and many other factors. And of course, when I am not being fed a proper VDD or a proper 0, I cannot deliver a proper VDD or a proper 0. So garbage in, garbage out. So this is why we have to be very careful about the design of our circuits. So here we are showing from Lucent Technologies, yes, for 60 Hertz. This is outside the chip. So typically the chip is packaged well enough to resist external noise. Hopefully, if we have a protective ground, maybe we will have a protective shield. Okay, what we are talking about here is we are talking within the chip itself. If we have, for example, wires going everywhere to different locations feeding signals. The signal in the middle is my victim signal, we call it, and the red ones are the aggressors, and we will talk about them later in the course. And this is the victim. And let us say that here all of these signals, what they have is, let us say that they have as input 0, but it is, and this also has as input 1. Let us say that this has a 1, and this is supposed to 0, and this is supposed to be 1. And let us assume that the aggressors on this, sorry, pardon me, let us assume that the aggressors on this are now glitching. Yeah, the signal is changing, and so the aggressor is having the input going down, and therefore the input here going up. And the same for this guy, this is going up. What happens here, you have two signals around you that are going up, and you're supposed to be 0. It's exactly like a car standing still in the road, okay? And then two cars coming next to it, around it, and moving fast. They're gonna shake the car and try to pull it with them, okay? So what's going to happen is that the capacitance is going to cause a glitch on the signal. Later, very much later, we're gonna explain this. So, but what I want to show is that this problem is getting worse with technology. And here, for example, the 0.35 micrometer technology, which was long time ago, the glitch was very small. But when they went up to the 0.12 micrometer technology, the glitch was high enough and it became close to VDD. And even it became wider. So we fear that if this noise is large enough, it can be latched or it can trigger a change in the circuit behavior. فإذا crosstalk is very important. We need to care about it. We need to understand the parasitics and the capacitance. طبعا it's a little bit complex, so I'm not explaining it now, but I'm just giving you how it relates to real world problems. Okay. طيب great. حدا عنده سؤال شيء على الكروستوك؟ اوكي طيب اوكي طيب خلينا هلا how can we understand whether my circuit will be relative to noise reliable and robust? نحن what we're going to look at is we're going to try to characterize the circuit. يعني we will try to figure out its steady state behavior and what you have learned before about the noise margins, and see how noise tolerant is my design. To be able to see how noise tolerant is my design and how well it can give me the logic 0 and the logic 1, we start by looking at the static or the steady state behavior of the gate. يعني I have a certain gate, I give it a specific DC input. What is the response DC output for this gate? Or I give it an input and I wait for a long time and I see how it responds to this input. This steady state behavior will tell us how robust the circuit is with respect to the noise. Okay, and let's go back to our basics. Digital design, we care about binary or Boolean variables, binary operation or Boolean variables, and therefore my input and output pins are supposed to represent a value which is 0 or 1. Okay, so this logical variable x, which is a 0 or a 1, will be associated in a regular circuit, will be associated with some voltage value. Yani for example, in the inverter, I will have 0 or VDD, and these will represent for me the logic value 1 or the logic value 0. Hello. Different designs might not be able to give me a perfect 0 or a perfect VDD. Okay, so these designs, we will refer to their voltage levels as VOH to represent a value which is VDD minus, and VOL to represent a voltage which is 0 plus or slightly above the ground. Okay, and those nominal voltage levels, this will represent the logic 1, and this will represent for me the logic 0. يعني أنا if I want to have a logic 0 and I want to have a logic 1, my circuit has to attain some voltage level representing those states. Okay, now therefore my circuit is going to swing between VOL and VOH, okay, and it might drop and stay there and then rise again, and this range between VOL and VOH we call it the logic or the signal swing. يعني الفولتج level عم يقلب بين هالتو levels. Okay, هلا. So what we are showing you here is that what we are showing in this here is that the circuit will have VN and Vout, okay, and therefore really VOH is the nut of VOL and VOL is the nut of VOH. هلا هيك لنشوف ليش بنحكي عن why we talk about VOL and VOH. ما أنا I can supply VN as 0 and Vout as VDD, right? But let us see what happens here. هات نشوف if we look at two inverters back to back. Okay, so the circuit has depth and I can only supply my input to the primary input pins of the chip. Okay, so if I take it for granted that this curve that is shown here, which is the voltage transfer characteristics representing VN versus Vout is given to me, I will start by looking into this. I am going first to provide an input which is 0 here, okay? So if my input is 0, my output will be what? VOH, okay? And if I input here a signal which is VDD, which is here, let us say this is VDD, okay, then my output will be what? VOL. So the output will be VOL. So although for the first stage I provided 0 and VDD, the input to my next stage now is VOL or VOH. And therefore now I am going to see that for inverter number 2, okay, so for inverter number 2, now when my input is VOL, let's see, so when my input is VOL, my output is going to be VOH, and I'm going to call this point A, okay, and then when my input is VOH, which is here for inverter number 2. So when my input is VOH, my output is VOL, and this is going to be point number B. Okay, so therefore inside my circuit, I have VOH and VOL now, and they are inverting, yani VOH is becoming VOL and the VOL is becoming VOH, so on and so forth. Okay, so this is why we care to solve for these two metrics, because we will see later that my circuit can only sustain those values and those values will propagate inside my design. هيدول two important points. One other important point for the circuit is the point where Vin equals to Vout. Okay, so the point Vout equals to Vin, and it is equal to Vm for this circuit. So at this point, Vm, the input is Vm, and the output corresponding to this point is Vm. We call it the switching threshold. and it tells us how good the inverter is. It tells me how good the inverter is. Now, I see a question from Paul regards what does VDD over 2 give as an output in the circuit. So, Paul, depending on the circuit design itself, VDD over 2 is going to fall somewhere. If the circuit is designed perfectly symmetric, VM will be equal to VDD over 2, and it will give me a VDD over 2. And we will see that this is a forbidden region for operation in the inverter. We don't want to operate there. We will define now where are the ranges for the logic 0 and for the logic 1. Okay, Hela, why we care for the switching threshold? Because we care to know, when we study the voltage transfer characteristics of the inverter, let us say that an inverter transfer function is like this versus another inverter transfer function is like this. These are not symmetric inverters. We don't want them because the top one favors the high state and the lower one favors the low state. And therefore, they will be susceptible to noise for the other state. Okay, so these are not symmetric, but if we look at this, V out equals Vn. If we draw the VDD point, it will be higher, and this one, if we draw the 50% point, it will be lower. يعني Vn equals V out point, sorry, it will be lower, and therefore we know that this inverter is biased to one operation versus the other. So we try to make it as symmetric as possible, and the switching threshold helps us in making sure that that is the case. طيب عرفنا فإذا VM, we defined VOH and we defined VOL. Let us jump to the second slide to start to look at, mapping the logic levels to the voltage domain. طيب, can I operate in all of this range robustly? No. Okay, so in order to be able to robustly operate, we define acceptable regions, acceptable 1 and acceptable 0 voltages, okay? And to define those ranges, we define two quantities, V input high and V input low. And the V input high and the V input low occur at the points where the slope of the voltage transfer characteristic curve equals to -1. Why? Because this tells me that dVo by dVn equals to -1. And this means that any noise or signal that arrives here will not be amplified. Okay, if it gets amplified, it will take me to the other side of operation. I don't want to amplify it and get an output low versus an output high. So this region between those two is forbidden. I don't want to operate in it. Okay, let us look at the gist of it. If I have an input signal and this input signal has noise, and let me assume that this is Vn versus time. Okay, so this is the time axis and this is Vn. And let us assume that Vn, instead of being perfect VOH, it has noise and it has here noise. Okay, let us say that this noise is delimited by VIL and delimited here by VIH. Okay, so if I take any point on this graph, okay, any point here, so long that my point is below VIL, the corresponding output will be approximately VOH. So this means that my output here, VO as function of time t, is going to be very close, maybe with some glitches, to VOH. Okay, and then let me take a point here, any point here, so long it is higher than VIH. So any point here will give me an output that is very close to VOL. So therefore, my output is going to be very close to VOL. So long my input is fluctuating below VIL or above VIH, it can represent to me logic 0 or logic 1 perfectly without having the noise affect me. Okay, so فإذا logic 0, it is represented anywhere the input is between VOL and VIL. هيدي بتمثل لي الزيرو. And if the input is between VIH and VOH, this represents the logic 1 for me. Okay, فإذا logic 1 هي بين VIH و VOH, logic 0 is between VIL and VOL. فإذا نحن we can say that the logic 1 هي بين VIH و VOH, and the logic 0 is between VIL and VOL. Okay, صحيح هي ال VO is an output quantity, but it is an input inside the circuit, and this is the range that we care for. Anywhere in between, the noise will be amplified, and I will end up getting an output that might be low instead of high, and I cannot handle it. Okay, so let us see here the kind of definitions that we have on the slide. So for my slide that I have here, if we look, they drew for me that the input is going to be between VIH and VOH, it's logic 1, and between VOL and VIL, it's logic 0. Of course, I can go all the way to 0 or all the way to VDD if I have primary inputs. Anywhere in between, this is forbidden. We don't want it. Okay, we don't want to operate in it or have the noise be there. Okay, فإذا this is a summary of the chart. We want the 0 and the 1 intervals though to be as large as possible. يعني أنا if I can increase this range, this will be perfect for me. Okay, so هلا we bring two definitions with us from 310, which are the noise margin high and the noise margin low. So for the noise margin high, it is VOH minus VIH, and the noise margin low, it is VIL minus VOL. The larger these margins are, the smaller the forbidden region is, and the more noise my circuit can tolerate. So we have to design the circuit parameters to increase these noise margins. Okay, so these are the noise margins that we learned before. Let us look at the circuit. One property that we care for is the noise, the regenerative property. Okay, so let us understand what's happening here. So V0 is a signal that barely meets VIH, okay, and VIL. يعني, if we assume that these two lines are VIL and VIH, V0 is on the good side, but it is not very high. What happens in the circuit is that although this is a weak this is a weak signal, and it is a bad low or high. If we look here, the weak high will give me a better low. So this is a weak high, will give me a decent low at V1, and then at V2, the high will go back to normal. So this is a good high. So the circuit is regenerative, يعني هو by nature, it can correct the signal as we propagate in the different layers, so long we are within our noise margins or the signal satisfies that it falls in the range of above VIH or below VIL. Okay. This is the conditions for regeneration. Typically come from the properties of this curve. Okay. And the properties of this curve are as follows, the voltage transfer characteristics. We have to have a gain that is greater than 1, okay, in the middle region, and it is bordered by two valid zones where the gain is smaller than 1. So here the gain has to be greater than 1, and here in those two regions, the gain has to be smaller than 1. Okay, so long we have this property, then my circuit can recover quickly. Okay, then my circuit can recover quickly. Okay, so let us now look at the following slide. Okay, so the noise margin expresses the ability of my circuit to overpower the noise, and the absolute noise margin sometimes can be deceptive. So this is why we need to take care of our circuit as is, because sometimes I might have a floating node. كيف يعني floating node? هيدي node is driven by a switch, okay, and a resistor to VDD, okay? So if it is subject to noise, the switch can help recover it, but the other node has the switch open and it was charged before. So if it is subject to noise, I cannot recover, whether pulling down or pulling up, I cannot recover the value because nobody is really helping it. So this, we call it a floating node because nobody is really trying to pull it back to its true state. Okay? So noise immunity is our ability to suppress the noise. Great. هلا في شغله كثير مهمه بالدايركتيفيتي للنويز يلي هي انه the gate must be unidirectional. هيك لنشوف what this means. So if I have a transistor, if you recall well, the input arrives at the gate. There is some oxide for the capacitance to control the gate, and then the current travels from the drain to the source through the channel. Okay, so this same transistor is sitting here inside an inverter. Okay, and when we have the noise in case number 1 arrive at the drain node, let us say there is some noise, the noise is arriving here, the noise will affect the source node because of the current flow, how the charge flows, but it will not affect the gate. So the noise that is flowing here will not affect this node. Therefore, in the inverter, if the noise pops in here, it does not travel backward. It will affect this node and it can propagate forward to the next stages. That's why we say we want our circuits to be unidirectional لحتى نخفف impact of the noise flying in different directions. Okay, هلا let's look at the ideal inverter. What is an ideal inverter? The ideal inverter has infinite gain. Okay, it has the threshold or switching threshold lying exactly at VDD over 2 or in the middle of the logic swing. It has very high, it has large noise margins, which are practically equal to VDD over 2, okay? And it has infinite input impedance and zero output impedance. We'll talk about these later. But what matters to us now is to know what are the characteristics from a noise perspective. طيب, great. هلا we're going to talk about the fan in and fan out of a circuit. What does fan in and fan out mean? Okay, so fan out means the number of load gates connected to the output of my gate. I am the driver, I am driving this load, and the fan out represents the number of load gates. So in this case, the fan out is equal to how much? It's equal to 4. Okay, thank you, Paul. And then we will look at another definition, which is the fan in. The fan in is the number of inputs to my gate. Okay, and typically if my gate has a large fan in, it will be bigger and slower. So if the load is large, it will slow me. And if I am designed to have large inputs, I will be bigger. And therefore, I am not very much preferred. So that's why in design they define limits for the fan in and fan out. طيب great. هلا now that we know that a gate has a load and it can be large, we have to have a metric to measure the speed of this gate, and this metric is the performance metric or delay. You have seen this definition before. So if I have an input waveform Vn, okay, I define the delay in terms of how the output is switching. يعني here the output is switching from high to low, okay, so I call it TP high to low. And the TP high to low delay is the delay from 50% input to the output reaching its 50% value. In a similar fashion, for the other transition, we define for the other transition, we define the TP low to high, which is the output going from low to high, and it's the time from 50% input to 50% output for that specific transition. Please انتبهوا للدefinition منيح, and when we start talking about delays, we will ask you TP high to low. Make sure to know that it is related to the output signal. هلا, the total propagation delay is the average delay of the two quantities, TP high to low plus TP low to high over 2. Great. Hala. In addition to this, we define two metrics, which are the rise and fall time of the signal. Let us see what is the rise time and the fall time of the signal. So the fall time is the time it takes the output to drop from 90% VDD to 10% VDD, okay? And the rise time is the time it takes the output to rise from 10% VDD to 90% VDD. Okay, so these are three definitions that we care for. The delay 50%, with rise and the fall time. Why we care about them? Because engineers know that the delay is function not only of the load, but it also function of the input slew or the slope of the signal that is arriving to my circuit. Okay? طيب, great. Let us look at this circuit. حدا أول شيء عنده سؤال على the previous slides? Okay. خلينا نركز هون. Let us focus a little bit. This will be the last thing that we will cover for today during the lecture. Let us focus on this circuit because it will follow us for the delay analysis later when we study the complex logic gates. I have an RC circuit. This is a first order RC network. The input is switching from 0 to 1. I have to define what are my initial conditions at the output. So V out will have an initial voltage. This initial voltage is supposed to have been either given to me or I detected from the input initial state. So V initial at the output in here is 0. And what is the final expected voltage for the output here if the output is rising to the level, if the input is rising to level V? So the input is switching from 0 to V. The output is supposed to reach exactly V in the final state. It's supposed to follow Vn. So the output signal is going to follow this waveform. So this is V out. It's going to go all the way from 0 and then it will reach V at t equal to infinity. هات لنشوف. At t equals 0, this is the equation that they provided me. The output is equal to 1 minus 1, 0. And as t tends to infinity, V out will be equal to big V. Okay? Hello. Here they are telling us, and we will derive the equation, they are telling us that V out of t is equal to 1 minus e to the minus t over tau times V. We'll see how it is derived. And tau is nothing but the RC time constant of the circuit. Okay? From this quantity, they derive that the 50% delay for this specific circuit is 0.69 tau, and that the rise time, or the 10 to 90%, is 2.2 tau. Hella, I'm going to derive this for you. The two quantities, I'm going to derive them for you. Okay, so let us see how we derive these quantities. Great. Now we learned in previous courses that we can write the equation of V out in general, that it is equal to V final plus V initial minus V final times e to the minus t over tau. Okay, great. Hella, why is this the case? Because at t equal to 0, V out will be equal to what? هيطلع معنا بيساوي، هيطلع نشوف V final plus V initial minus V final times 1 هيطلع بيساوي V initial. And as t tends to infinity, V out is going to tend to basically V final. Okay, so هيدي equation بدنا نتذكرها. We need to remember it. Okay, so this is an important equation that we want you to remember. Great. هلا, for our case, we have V final equals to V and V initial is equal to 0. This implies that the equation for V out is equals to V plus 0 minus V times e to the minus t على tau. Now I can make this look like V into 1 minus e to the minus t على tau. هيدي الدريفيشن للإيكويشن. Okay. هلا حدا عنده سؤال على هاي الإيكويشن؟ Anybody has any questions? Okay. طيب, let us now look into this derivation of the delay. اجى قال لي انه V out of t is equal to V into 1 minus e to the minus t على tau. At 50%, he wants me to find the 50% delay, and I know that the graph at t equals 0 can output 0, and then it will eventually reach V at infinity. Okay, so the 50%, if my input switched at 0, okay, then the 50% delay will be when the delay will be t 50% minus 0. Okay, great. So at 50%, here is what I have. V out will be equal to V over 2 will be equal to V into 1 minus e to the minus t على tau. Okay, I will take this equation and solve for what I need to solve now for t. قديش هي هالتي that I need to solve for. So this, I do the math, sorry, I will do the math, and we will get that half is equal 1 minus e to the minus t على tau. We exchange, so e minus t على tau is equal to 1 minus half. وبيطلع عنا آخر شيء ناخد logarithm للboth sides. Okay, نعمل اللين للboth sides. Okay, so this will be minus ln 2 equal minus t على tau. وبتطلع عنا إنه t is equal to tau times ln 2. Okay, هلا this is, we solve for the 50% delay اللي هي 0.69 times tau. Okay, if we want now to solve for the rise time, we have to repeat this for two quantities. وهيك لنشوف شو هن هو two quantities to solve for the rise time. أول شيء نحن هلا بالرد حلينا لل 50%. أوكي، هلا نحن حنحل بالبلو لل 10 time to reach the 10% and the time to reach the 90%. Okay, so this is the 10%. And this is the 90%. هيدي حنسميها T1 وهيدي حنسميها T2. And then we will say that T2 minus T1 هي T rise يلي بتاخدنا من 10 ل 90%. Okay? We repeat the same. يعني we will to solve for T1, we will say that V out at T1 is going to be equal to 0.1 times V, and this is equal to V into 1 minus e to the minus t على tau. Okay, ومنحل T, we try to solve for T1. Okay, and the same we try to solve for T2 using a similar equation, and then we subtract the two quantities and we will be able to find what was disclosed here إنه T هي تطلع معنا آخر شيء 9 times tau. Okay, anybody has any questions about how we can derive T1 and T2? Okay, so for T2 حنجي نحط 0.9 V is equal to V into 1 minus e to the minus T2 على tau، ورح منحل وآخر شيء رح ناخد الدلتا لنطلع ال TR. Okay, طيب anybody has any questions? طيب, we will stop here today and I will upload those notes, and next time we will pick up and talk about the ring oscillator circuit. Okay, it is important because it is related to part of the project questions lithium analysis. طيب, thank you very much for your attendance. Thank you.